This chapter is about soil classification, where we group soils of similar behavior and develop ways to describe them. By forming such groups, we can generalize their properties and study them better. Major soil groups, based on the grain sizes, are shown here. The size cutoff limits are slightly different for USCS, BS, AS, IS and so on. USCS is the acronym for Unified Soil Classification System, used worldwide. Coarse-grained soils are those where the grains are larger than 75 microns, which includes sands and gravels. Here, one can see the individual grains. Fine-grained soils, where grains are smaller than 75 microns, include silts and clays. Here, we will not be able to see the individual grains by naked eye. Granular soils are also called cohesionless soils, which includes gravels, sands, and silts. Clays are non-granular soils, also called cohesive soils. Grain size distribution is knowing what grain sizes are present in what proportions, which is important in coarse-grained soils where this controls the soil behavior. We use sieves in coarse-grained soils and hydrometer and fines to determine the grain size distribution. In fine-grained soils, grain size distribution is not that important. To determine the grain size distribution, we use a set of sieves in a coarse-grained soil and hydrometer in a fine-grained soil. Sieves are round trays with a mesh at the bottom. The mesh openings are known by the diameter of the openings or numbers like 10, 20 and so on. Number 10 sieve means there are 10 openings per inch both ways, that is 100 openings per square inch. 3 sieves we use often are numbers 4, 40 and 200. Number 200 is the finest sieve we use, and the fraction passing number 200, which contains only silts and clays, is taken to a hydrometer test. Note the terms percentage passing, also called percent finer than, and percentage retained. The percent passing and percent retained are both cumulative. 59% passing 0.425 mm means 59% of the grains will pass through a 0.425 mm sieve. Hydrometer measures the density of the liquid in which it floats. In a soil suspension, larger grains settle early and the density of the suspension decreases with time. We measure the density of the suspension with time and translate the readings into grain size versus percent passing. We use Stokes' law, assuming the grains are spherical, for this conversion. Here we combine the sieve and hydrometer data to plot the grain size distribution curve. D10 is a grain size, corresponding to 10% passing, which in this case is 0.085 mm. That means 10% of the grains are smaller than 0.085 mm. Similarly, we can define D30, D50, D60, and so on. D50 is the median grain size, meaning 50% of the grains are smaller than this size. We define two terms here. The coefficients of uniformity and curvature, Cu and Cc, which define the shape of the curve. Larger value of Cu means there is a wider spread in the grain sizes. Granular soils are either well-graded or poorly graded. Uniform and gap-graded soils are special cases of poorly graded soils. In uniform soils, the grain sizes vary in a narrow range. Gap-graded soils have a gap in the grain sizes. Well-graded soils have a wide range of grain sizes and pack densely. The same granular soil can be packed at different void ratios. The extremes are the loosest and the densest. Here, we define relative density with a scale from 0 to 100%, 0 for the loosest and 100% for the densest. At the loosest state, the density is the lowest and the void ratio is the highest. It is opposite for the densest state. Here is the equation for the relative density, based on the void ratios. From the relative density in the range of 0 to 100%, we can call the granular soil as loose, dense, very dense, and so on. Here, you can see that the two soils A and B are at void ratio of 0.95. However, A is classified as loose and B as dense, because of their minimum and maximum void ratios. When the moisture content of a fine-grained soil is increased from 0%, the soil goes through distinct stages, namely, solid, semisolid, plastic, and liquid. The borderline moisture contents separating these states are the three Atterberg limits, SL, PL and LL. Plastidex is the difference between the liquid limit and plastic limit. It is a measure of the plasticity of a clayey soil. To determine the liquid limit, we can use either of the two devices here, Acos Algrandi's percussion cup or the Swedish Falcone. The first is used widely in North America and the second is used widely in Europe. Plastic limit test involves rolling the moist clay into a thread until it crumbles. If the crumbling occurs when the thread is 1/8 of an inch or 3 mm in diameter, the clay is at its plastic limit. Here, we try 5 or 6 moisture contents. For each mix, we measure the penetration of the cone as it is allowed to penetrate the soil paste freely for 5 seconds. Liquid limit is defined as the moisture content at which the penetration is 20 mm. If the fine-grained soil is at its plastic limit, if you try to roll it into a thread it crumbles when the diameter is 3 mm or 1/8 of an inch. Liquidity index is a number which says how close the current moisture content is to the liquid limit. Li equals 1 means the clay is at the liquid limit, 0 means it is at the plastic limit, and greater than 1 means the moisture content is more than the liquid limit. Clays I and B are at the same moisture content, however, their consistency differs significantly depending on their Atterberg limits. I is almost like a liquid, B is a lot stiffer and stronger. Think of a clay gradually losing moisture from its initial value W sub I, close to the liquid limit, until it reaches the shrinkage limit SL. It remains saturated and the void volume reduces. Further removal of moisture below the shrinkage limit makes the clay unsaturated with no further reduction in the void volume. Linear shrinkage is an indirect measure of the plasticity index, and the ability of the clay to shrink when dried. We have few different ways to classify soils such as USCS, AASHTO and some country-specific ones. USCS is the most used worldwide for geotechnical work. AASHTO is mainly for road work. Major soil groups we come across often are gravels, sands, silts and clays, denoted by G, S, M, and C, respectively. Sometimes, we also come across organic soils O and PEDS PT. We describe the coarse-grained soils as well or poorly graded, clayey or silty. Grained soils are described as high plastic or low plastic, depending on whether the liquid limit is above or below 50. Here are some simple rules we follow with USCS. 1. If more than half is coarse-grained, it is a coarse-grained soil. If more than half is fine-grained, it is a fine-grained soil. 2. In a coarse-grained soil, if there are more sands than gravels, it is a sand and vice versa. 3. Describe soils by a two-letter symbol XY, X for the major soil group and Y for the descriptor. 4. In a fine-grained soil, call it a clay if it plots above the A line and silt if it plots below the A line. In USCS, we assign the symbol based on the percentage of fines in the soil. The standard symbol is XY, where X is the major soil group and Y is the descriptor. Only when the percent fines is 5 to 12, we give a dual symbol as XY-XZ. Here is Casagrande's PI versus LL chart. All fine-grained soils must plot below the U line, U for upper limit, clays are above the A line and silts are below, depending on whether the liquid limit is more or less than 50, describe them as high or low plastic.
The soil classification we use in Australia AS 1726 is similar to USCS, with a twist. The three differences are, 1. Sand gravel cut-off is at 2.36 mm in AS 1726 as opposed to 4.75 mm in USCS. Similarly, the gravel's cobbles cut-off is at 63 mm, not 75 mm. 2. Soils with more than 35% fines, not 50%, are fine-grained soils in AS 1726. 3. Based on whether the liquid limit is greater or less than 50, we call the fines as H or L, respectively. In AS 1726, we have an intermediate class I, for liquid limit between 35 and 50.
Gravels or sands can be described as well-graded, poorly graded, silty or clayey. Fines are described as low or high plastic based on the liquid limit. The geotechnical engineer must be able to visually classify the soil without any test or equipment, and sensibly describe them. This is relatively easier for coarse-grained soils where the grains are visible to the naked eye. Here, we can say the soil is well or poorly graded, whether the grains are sands or gravel, and within that whether the grains are fine, medium, or coarse. It is also possible to include angularity of the grains and color in the description of coarse-grained soils. One can mention the presence of fines and whether the fines, and any state of compaction or cementation. Fine-grained soils are easily classified based on dry strength, by trying to crush a lump between fingers. Clays have high dry strength and silts have low dry strength. Wet clay feels sticky between fingers and wet silt feels gritty between fingers. Dilatancy can be tested to identify the fines. Hold a moist pad of fines on your palm and vibrate to see how quick water rises to the surface, making it shiny. It happens relatively quick in silts and slow in clays.